Hello everyone, today we'll be going over a system design course today, and today we're focusing on the concept of hash indexes. Now, since we're diving into the realm of databases, hash indexes are a key and vital important concept because they are analogous to dictionaries in programming languages. So they are similar to dictionaries where they offer a fast way to access the value of a known key. So access a fast way to get the value of a known key, to do a key value pairing. And the best way to metaphorize this or have an example, it's like lockers in particular and having a key. Hash indexes work by employing a hash function that takes the key and computes an index into an array of buckets or slots. So they employ a hash function by computing an index into an array of buckets. Buckets/slots. So it's like, for instance, if we were to go over our example between the lockers. So whenever we are searching for, in fact, I'm just going to use a different color for this, just to be able to draw the whole lockers example. So whenever we are scanning, in particular, any type of data structure within hash indexes, we're always keeping track of every single point of data that we have always visited in particular. Like, for instance, if we are going throughout every single locker we have, and we have a specific key that we need to find exactly where that locker is, and we're going to have to walk through this hallway of lockers, and we already know exactly which locker we have already visited because the key in of itself is not going to fit there. But when it does, that means we actually are able to unlock. So let's just say, like, I'm going to put a star right here for this key value pair. When the key actually goes up to this specific value and pairs it together, we're able to open the locker. So that's just an example to be able to help visualize this more, to be able to help us understand more about hash indexes in general. So in particular, if we have a desired value that we are looking for, it can be quickly retrieved with hash indexes. That is why they're useful in general. They know exactly which point of value that we're able to get while we're scanning throughout a different form of data structures. So even though the hash indexes are widely popular, they do have their limitations though. For instance, I'll just put in limitations. Since one, we got to visit every single locker, for instance, we're keeping track of every single locker that we have visited, so therefore we are storing memory for every visited component. Let me just move this really quick. There we go. And I'll move this as well. Okay. And so just as a result from having to store said memory at the same time, we are going to be constrained by RAM. So it's just something to keep in mind as well. And however, despite the limitations, they do have a wide variety of applications, but a key point to actually keep in mind is that they're not well suited for range queries that involve fetching a sequence of keys. But overall, they shine through situations where we're trying to find unique keys which can be accessed frequently, such as if we were to put this more in the system design example, a key example, just, or I'll just put it in the star example, or system design example. Yeah, there we go. For a system design example, that would be in a case where we are trying to access a cache that holds comp. Okay, so we're trying to find specific caches which hold queries. So it could be, for instance, if we are looking at some type of memory state, maybe, for instance, history of subscribers, for instance. On a YouTube channel. That could be one example that we have, since there is a cache in particular whenever we are refreshing a web page, showcasing exactly the data that we have already been interacting with on the platform. So let me just zoom out of this really quick. Clean this up. I'll just put this image here for reference and expand upon it. There we go. And feel free to take a screenshot of this part. And now let's move over to our concept example. And now let's go over a concept example. So in our concept example, let's imagine we're running a popular online music streaming service along with various stocks of sound. And for every single song/sound played, our service needs to quickly access the metadata. So we need to quickly access the metadata. And here, in the context of the hash index, it's great for retrieval. There we go. For hash indexes are able to fetch the song's details along with other layers of data. So able to fetch layers of data. And for instance, in the context of our locker example, whenever we open our locker, we're able to get our stuff in. And that can include books, journals, etc. We're basically able to get layers of data. And so in the context of the DJ and their music service, the key would be considered an ID. It could be the song's ID in particular. Like there's a specific key that they find whenever someone's searching through a specific song. And it could be the number of playback speeds or how many likes the song had. There could be forms of metadata that can be wrapped inside. And overall, we also got to note that as the library grows, just something to note. So overall, as the library expands, so does the index. Because we're storing every single visit. Storing each visit, I would say. That's probably the best way to do it. phrase it. And in order to avoid running out of memory, there's a technique called the log structure, where the log structure, as indicated by these two images over here, organize the data into playlists, so to speak. Into playlists. That's the best way of describing it. These playlists in of itself, it's similar to, again, with the whole example that we have the locker, opening a locker, we have different compartments of stuff. Now, inside of our locker, we can organize the stuff based on whatever type. It could be like subject, activity, etc. Yeah, right over there. Now, if we want to go over in depth and further example between these two images right here. So namely, this is our data file segment, and overall, it's supposed to represent of how data file segments are supposed to be performed and entering different labels. So if we have different sounds, so this is a sound data file segment. There are entry labels that we have, such as mu, or per, or yawn, and they are followed by a number. These labels and numbers likely represent data records of keys in a hash index. So keys in a hash index. And overall, these are the compacted segments that can expand more on exactly the different data files that are inside. So it's kind of like, again, like a dictionary per se. Going over what we have, if we want to go for a word with a specific letter, that's a good way of phrasing it up. So the first part of the image shows a compacted process where a larger data segment is comprised into a smaller one. And this typically involves removing deleted or obsolete entries to save space and improve performance. And hash indexes are widely used in operating systems as well. Sometimes there might be some files you've never opened before, and there will be a hash index that would actually encrypt some of the files as well throughout as less files become irrelevant, since one has not opened them in a while, if they're storing them particularly on their desktop or system. Some operating systems do that. So if we were to go off on our second part for our image, we will always have to keep in mind of the different entries that are compacted into a single entry, and how whenever we update a given number inside of the data file segment, the following compacted segment would also reflect that as well. Now, if we were to expand this upon more, where we have different data file segments, is that these different data file segments actually merge data files 1 and 2 together, and then we will have some entries that are removed and combined, as seen with mu 1087 and then per 2114 being the remaining entries after the merging process, along with yawn and scratch. So could see more. Yep. Right. So overall expands upon different file entries. Let's just move out of here. Let me just clean this up here, folks. There we go. Just move out of here. So this was our concept example. Feel free to take a screenshot of this one. And let's move on to our first practice problem. And now let's go over our first practice problem. So in our first practice problem, we're going to be looking at a bookstore hash index, namely. So what we will be doing is that for our first practice problem, we're overall taking the role of a database administrator. Let's go database admin. And overall, what we're doing is that we are storing catalogs of books with a unique identifier. So I'm just put an ID, and typically that would just be an ISBN. And we currently have a hash index in memory for quick access, but as the inventory grows, as usual, as inventory grows, so does the hash index. And that will also pinpoint the idea of memory constraints. So the steps for us to be able to help or to solve through this, let me just go through this. I'll zoom in a bit. Steps for us to be able to solve this and go over what we need to do. One, we need to understand segment files. Second part, implement compaction. The third part being optimize partial index. And the fourth part being we have to do a log cleanup. There we go. And so we also have corresponding code at the same time. So these are the following tables that we have already made, and this is all in SQL, namely. So just putting it for reference out there. The first step when we have to understand the segmenting files, and whenever we look at using a hash index for the ISB column, what we're doing is that we are looking through a database. Based on ID. And that's typically ISBN. That means we have to know exactly what the ID is going to be. Then whenever we implement compaction, indicated in step 2, let me just zoom in a little bit over here. So that means we are deleting books from the table, books that we have up here, where the ISBN is not in, and then we select the ISBN from the current inventory. It's pretty self-explanatory. And we regularly remove obsolete entries to maintain compactness. So we remove obsolete entries for compactness. The third step being we need to optimize partial indexes. And whenever we do so, we are looking further in depth within step 3 to maintain a partial hash index on frequently accessed data. So whenever we are looking through, we're looking at frequently accessed data. And then whenever we are doing the log cleanup, so we clean up the logs to prevent outdated indexes from consuming memory. And so when we have done so, it's sort of like how step 2 and 4 are already coinciding with each other. So we delete outdated indexes and index logs to only focus on the most recent and frequent search data via hash indexes. Let me just erase and zoom out more. There we go. And moving out, let me just zoom out fully for you folks and actually expand more on these images. Let me move this and then be able to showcase more. I'm just going to make the code larger. There we go. All right. Now, feel free to take a screenshot of this practice problem, and let's move over to our second practice problem. For our second practice problem, let's consider applying our knowledge for an online video game store. So in the store has a digital library where each game has a unique code. So each game in the store has a unique code to the metadata and corresponding memory in the hash map. So we map game codes in metadata and correspond with in memory hash map. So if we were to go over all the steps that we need, it's going to be the same thing that we did before, but to be able to further cement. So 1, we would understand the segmented files, understand segment files, which usually means that we need to know exactly the ID. And Again, same thing in context. These are our tables. These are our steps needed to be able to implement our hash index. And the second step is implement compaction. Third step being optimizing partial indexes. Then with the fourth one being log cleanup. For our first part, we already know in particular that we have to know the ID that we're going to be associating with, and it looks like it's just going to be the game codes that will be associated with each game. And then on the games table that we would have and implement a hash to get the game code. And then in the second part, we implement the compaction. Let me just clear this up. When we do so, we are deleting the indexes that are no longer sold or supported. So here over here, so no longer supported. Then the third one, optimizing the partial indexes. That means we are prioritizing saying the most sought or searched index, and then we purge the outdated logs. So technically, between hash indexes, it's more of, so hang on, let me just write this here. So implementing compaction means delete the old non-supported games, optimization partial indexes, prioritize the most frequent indexes, and locking up, purge the outdated logs. Technically, there are 2 points with hash indexes, so let me just zoom out. One, we always talk about the unique identifier. And the latter part being the pathway to get to the ID and what is the most efficient. So if we were to go back in the locker example, you would typically have one locker, and out of habit, you would take one path to get to the locker, or you could take multiple paths, but the most frequent path, take the most frequent path to get to locker. And then typically you would just be unlocking that locker. The other paths to get to the locker would be forgotten. Because they're not used. And not just the paths, which would be considered the logs, but also every other locker we have seen that we won't see. So, and every other unimportant locker we don't interact with. There we go. Let me just clean more of this up. And clean up this stuff fully. There we go. There we go. Okay, and feel free to take a screenshot of this. And yes, this was our system design video lecture series focusing on hash indexes. Thank you again for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.